Hello and welcome to this lecture. In the previous lecture, we introduced this notion of inner product and norm and saw how this natural notions of dot product and length you've been defining in Euclidean spaces extends very naturally to abstract vector spaces as well. And we saw some basic properties of inner products and norms, how they are related, etc. Now we will start using inner products and norms in the main problem we have, right? So how to understand operators. So we had vector spaces before, now we have inner product spaces. How do you better understand operators in inner product spaces? Most of the applications we would deal with would be in an inner product space. So in an inner product space, can we say more about operators? So if you remember before, we came up to eigenvalues, we show operators had eigenvalues, eigenvectors, and some of them could be diagonalized, all of them had an upper triangular matrix representation, all of that was true in any vector space, right? So now that you have inner product spaces, can we say something more special? Can we think of operators more clearly? Can we classify them? Can we understand a lot of these properties? Okay, so that's what we're going to start doing, and the crucial starting point is this notion of an orthonormal basis and this notion of Gram-Schmidt orthogonalization. So these things help a lot. Okay, so let's get started. Okay, a quick recap. We've seen all of this before. What we saw in the very last lecture, the previous lecture, was this notion of inner products and norms and orthogonality and related properties and very nice results based on inner products and norms, particularly the Cauchy-Schwarz inequality, very nice inequality which relates inner products and norms. Okay, so we'll make a very small definition which is look like a simple definition, but it will have a lot of interesting simplifications will happen in our understanding of operators when we do this. So throughout this lecture, we'll think of V as an inner product space. Maybe one or two times we'll not have that assumption, but mostly it will be an inner product space. I will call a list of vectors E1, E2 to EM as orthonormal if the two conditions are satisfied. What are the two conditions? One is ortho, one is normal. Normal means the norm is 1. Okay, so that's sort of like the way in which it's defined. And in this sense, orthonormal, normal sort of implies the norm is 1, and ortho means any two vectors, two distinct vectors have an inner product of 0. Okay, so basically it just says ei comma ej is 1 if I equals j and 0 if I is not j. Right, so that's what this also means, right? So that's the notion, because we know that the norm comes from the inner product. All of that is assumed here. Since that is true, this is definition. Okay, so this orthonormal list of vectors, do they exist? Can you come up with an orthonormal list of vectors? I mean, naturally you might ask these questions, but what is the benefit of having orthonormal list of vectors? What's the big deal with orthogonality? Okay, so we'll see they simplify a lot of things. We'll start looking at initially some simplification. As we go further, you'll see the power of the orthogonality and simplifications entering the picture. Okay. Here are a couple of basic examples just to motivate and convince you that orthonormal vectors do exist. Okay, the standard basis is a standout example. Okay, so immediate example, you quickly see that orthonormality is satisfied for the standard basis. It's very easy to convince yourself that that's true. Here is another example which is maybe slightly more non-trivial. Okay, so you see 1 by root 2, 1 by root 2 and 1 by root 2 minus 1 by root 2. So this satisfies all the conditions that we have. Each vector is unit norm, and I mean, I'm thinking of the 2 norm here. Okay, so in this thing, it's a Euclidean 2 norm. Okay, so it's got unit norm and dot product is 0. So familiar dot product is what I'm using. Okay, so this is orthonormality. Okay, so there's a connection between orthonormality and linear independence. Okay, and also orthonormality simplifies things when we look at things. Okay, so let's look at why that is so. Here is a very nice result. Okay, if you have an orthonormal list of vectors and you do a linear combination of them, okay, I do a linear combination with the orthonormal set, okay, a1 e1 plus am em. So as are scalars. Okay, so maybe I should mention that here. Ai's are scalars. Okay, so you do a linear combination with the orthonormal list of vectors and you look at the norm square after the linear combination. Okay, so maybe you're thinking, it's a linear combination, I have to use the properties of the inner product, etc., etc. But remember, all of them are orthogonal. If you use those properties and you start cancelling out, etc., you will simply directly get sum of the absolute value square of the AI. Okay. So, it is a very easy and simple result. So, you see already that linear combinations are very simple to deal with when you think of orthonormal vectors, and so that is at the heart of a lot of simplification in our understanding of linear operators. Okay. So, proof is very easy. I do not want to go into details. You just write it as an inner product of this vector, the linear combination vector with itself, and then expand it out. A lot of cross terms will cancel, the same terms will simply give you value 1 and you will get the answer. Okay. Here is another result. Okay. An orthonormal list of vectors, orthonormal set of vectors, they are also linearly independent. Okay. So, it is quite easy to see, the proof can come directly from above. Okay. If it turns out the linear combination is 0, then their norm is 0, which means each of the AI squared absolute value is equal to 0, each of the AI, and AI is 0. Okay. So, that shows that a set of orthogonal vectors or orthonormal vectors, they are also linearly independent. Okay. So, you immediately see the connection there. It is not very difficult to imagine. You can have linearly dependent set which are not orthonormal, that is possible. Okay. So, it is not if and only if or anything. There are very many linearly independent sets which are not orthonormal, but orthonormal sets are linearly independent. Okay. So, this immediately gives you a lot of restrictions. So, if you have finite dimensional vector space, how many orthonormal vectors can you have? As many as the number of basis vectors, right, the dimension. Dimension limits the number of orthonormal vectors that you can have as well. Okay. So, these are all nice results that come about once you identify the connection between linear independence and orthonormal set. Okay. So, you see that orthogonality is linear independence and more. Okay. So, it gives you linear independence, but it also means the dot product is 0, right. So, that gives you more stronger characterization of basis vectors maybe. Okay, right. So, that is interesting to have. Okay. So, this leads to the definition of an orthonormal basis. Okay. An orthonormal basis for an inner product space V is simply what the name says. It should be a basis and it should also be an orthonormal set. Okay. So, now that we know that an orthonormal set is also linearly independent, it is very obvious that if you have a finite dimensional vector space V and the dimension is n, and if you produce n orthonormal vectors, right, then that forms a basis. So, we see that this orthonormal basis is going to be something that is really very interesting, right. So, when you have an inner product space, this is what distinguishes the inner product space from a space without an inner product. You can have an orthonormal basis. Okay. You have the possibility of an orthonormal basis. So far we have not shown that there exists an orthonormal basis, we have only shown one can even at least conceive of an orthonormal basis. Okay. And we see that orthonormality can give you a lot of simplifications, particularly expressing vectors in terms of an orthonormal basis will end up being very nice and simple and elegant, and they are connected to the inner product and all that. We will see that soon enough in the next few slides. So, are there orthonormal bases? Yes, definitely. Right. So, you can immediately come up with an example. The standard basis is an orthonormal basis, right. In any vector space that we have taken so far, R and Cn, you take the standard basis, it is an orthonormal basis. So, orthonormal bases do exist, they are there, but are they there all the time in a product space? We do not know that yet, but they are there at least. There are at least 1 or 2 examples. Okay. I will give you one more example, maybe it is not immediately obvious, but this is an R4 and you can see this is an orthonormal basis, right. So, you can check for yourself that any 2 vectors are orthonormal here, and you can do the calculations if you like, and at the same time they are all unit norm. This is R4, right, and I am doing the dot product and usual 2 norm. Okay. So, this is an example. So, there are looks like there are many orthonormal bases. We will see soon enough that there are indeed orthonormal bases, but orthonormal basis looks like it exists. But what is the advantage? Are there advantages? Are there simplifications in using an orthonormal basis? It turns out yes. Already if you just think in terms of coordinates, you will see an advantage, and then when you think in terms of operators, you will see there are more interesting advantages. Okay. So, first thing is, if you think of an inner product space and you have a basis E1 through En, if you ask me what are the coordinates of a vector V in the above basis, I do not have an easy way to establish this, right. So, you have a V and then I have to write down some equation, I have to see how to express this, maybe a matrix equation, maybe some linear equation solving, all sorts of things are needed if I do not have orthogonality. If you have orthonormality, look at what happens. If this basis is orthonormal, all you have to do is evaluate inner products. Okay, you take your vector v, you evaluate inner products with each of the basis vectors and do a linear combination with them, you will get v. Okay, so it's very, it seems like a very intuitive and easy result. Maybe you learned this in so many ways in the previous classes, but one can prove this quite easily. Okay, so v when expressed, okay, in the basis E1 to En. Okay, first of all, it's a basis, so you know that v can be expressed as a linear combination of E1 to En, and after that, it's a very easy exercise to show v inner product with E1 is simply the first coefficient, v inner product with En is the last coefficient. Not only that, we saw before that the norm of v is simply the norm square of, mod square sum of each of these coefficients. Okay, so all this is very nice. So expressing a vector in terms of an orthonormal basis is very, very trivial. You simply what's called project onto that each of these basis vectors, take the inner product with each of these basis vectors and simply scale them and add them, you get your answer. Okay, so it's an easy proof. I'll skip the details of that. Okay, so this has become simplified, but what else can happen with operators? That's also an important question. Okay, so far we've been sort of skirting the question of, do orthonormal bases exist? Are there orthonormal bases for a finite dimensional vector space? Can you find them? Are there easy ways to find them? And that's what's given by this Gram-Schmidt orthonormalization procedure. It's a very simple procedure. It sort of converts a linearly independent set into an orthonormal set with the same span, same incremental span. So I'll talk about why, how it works and why that is so shortly, but take that as an important definition. So basically, if you have a linearly independent set, this Gram-Schmidt process will output a orthonormal set, but with spans being the same. So at every level, spans will be the same. So it's a very powerful and very simple and elegant procedure. Okay, so how does that go? The input, like I said, is a set of linearly independent vectors in your inner product space. So the first thing you do is you take the first vector and normalize it. Okay, so this process of dividing a vector by its norm, it's called normalizing. So what happens after normalizing? The norm of E1 will simply become 1, isn't it? So that's a nice thing to do. So you can normalize, norm of E1 becomes 1. So this is called normalization. Okay, so notice this normalization. So dividing a vector by its norm makes the overall norm as 1. Okay, so you can quickly prove it. It's not very hard. Just use the homogeneity property and you'll get just 1. Okay, so this normalization will be one property. But normalization alone is not needed, right? So just because you do E1, and you can't say E2 is simply norm, V2 by norm V2. But then V1 and V2 will not be orthogonal. I also want the orthogonality, right? I want the output from this process to be orthogonal. So for that, we will use some sort of an orthonormal decomposition idea, and this is what will happen. So this is what the process does. Okay, so in general, for a particular j, this is the step. But let me just show you what happens for j equals 2. Okay, so that will help you. Let's go to j equals 2. You will define E2 as V2 minus V2 inner product E1 E1 divided by the norm of the whole thing. Okay, forget about the norm coming in the denominator. So that is just to normalize, right? So this V2 minus V2 comma E1 multiplied by E1, that is going to be this guy, the guy in the numerator is orthogonal with V1, with E1. Okay, so that's the crucial part. Okay, and that's very easy to show, right? So for instance, you can show V2 minus V2 comma E1 E1 comma E1, right? What will this work out as? V2 comma E1. Okay, just use the additivity property, minus V2 comma E1 times E1 comma E1, and E1 comma E1 is 1, so that ends up being true. Okay, so how do you prove the orthogonality? Simply by evaluation. So what's being done here, it's not very hard to imagine, right? So you're taking that same orthogonal decomposition approach. Okay, so you decompose V2 into a part that lies along E1, and then you subtract it out, you will get a part that's orthogonal to E1, right. So, that is the same orthogonal decomposition. I am just writing this down once again to show you that that is true. And then once I get the orthogonal thing, I simply divide by its norm to get E2. So, norm of E2 will be 1 and E2 and E1 will be orthogonal. Okay. So, that is the condition here. Now, what do you do for an arbitrary j? You take Vj and simply subtract the inner product of Vj with E1, E1 minus inner product of Vj with E2, E2 so on till Vj, Ej minus 1, Ej minus 1 and then divide by its norm. So, this process you can see every step will keep giving you normalized vectors norm 1 and at the same time all of them being orthogonal to each other. At every step they are orthogonal, 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 orthogonal. Okay. So, that is the nice little result. I mean, there is nothing more to prove here. It is a very simple process and you can take any set of vectors and try it out. It is very easy to prove this. Okay. So, the output E1 through EM is an orthonormal list. Not only that, okay, the orthonormal list part is easy enough to show, but notice what has happened here. This is very, very crucial. The span of V1 to Vj for every j is the same as span of E1 to Ej. Okay. This maybe takes a little bit of proving and you can prove it by induction, it is very easy. Okay. But the span is the same and it is not too difficult to imagine why, because E1 was proportional to V1 and E2 was V2 minus something, right. So, it was still the span will remain the same. Okay. So, this linear independence and the span does not change. Okay. So, this is crucial and for every j the span remains the same, not just the overall span. Okay. So, it is almost like the Gaussian elimination sort of process, right. So, there are these processes which are very important. First was that elementary row operations which helped you do rank and all that. Next was this upper triangularization with eigenvalues which helped you, do something, and here is an orthonormalization process. From linear independence you can go to orthonormal case also. Okay. So, the proof you can do by induction on J, particularly the fourth part, the last part, the span being the same, is easy to do with induction on J. I am skipping the details, you can see in the book also there are details of the proof, but you can see intuitively why this should be true. Okay. So, this process which is called the Gram-Schmidt orthonormalization procedure is very, very important. Okay. So, this shows you that there are orthonormal sets of vectors that you can easily generate given a linearly independent set. We know there are linearly independent sets. So, you take linearly independent sets, from there you can generate orthonormal sets. Okay. So, that is very nice. So, this also gives you many more results. Okay. So, particularly about existence and extension possibilities. Okay. So, supposing you have an inner product space which is finite dimensional, then that has an orthonormal basis. What do you do? How do you prove this? It is very easy. You simply take a basis for V. You know that there is a basis for V and you perform Gram-Schmidt. If you do Gram-Schmidt, you will get an orthonormal basis, right. So, you know that every inner product space now, if it is finite dimensional, it has an orthonormal basis. Next is an orthonormal list of vectors can be extended to form an orthonormal basis. Supposing you have a large dimension vector space and you have a few orthonormal vectors, a list of orthonormal vectors, you can extend them without affecting them, you can extend them to form an orthonormal basis overall. Okay. So, how do you do it? Again, you do the same method, right. You take the original orthonormal list, you know it is a linearly independent list, you simply extend it to form a basis, a general basis without worrying about orthonormality, and then you apply Gram-Schmidt on this whole process, right. What will happen when you apply Gram-Schmidt? The initial set of orthonormal things will not change. The reason is Gram-Schmidt is going to keep doing these dot products and all of them will remain the same. Okay. If you already have orthonormality, why will Gram-Schmidt do anything? It will not do anything. Only afterwards it will start making it orthonormal. Okay. So, you will have an extension also possible. So, this orthonormal basis in an inner product space is as powerful as a basis and as prevalent as a basis. Okay. There are orthonormal bases and you can take small orthonormal sets and extend them to form a basis. Okay. So, in inner product spaces you can happily have orthonormal bases. Of course, you also have other bases which are not orthonormal, but orthonormal is particularly interesting. When you have orthonormal bases, so many computations become easy, and you will see later on also many more computations will become easy for you in an orthonormal basis. So, as far as possible you should try to work with an orthonormal basis, and only when orthonormality does not make sense you should move away from it. Okay. So, this is a very useful principle when you deal with vector spaces and operators. Okay. So, this is, and they do exist, extension exists, orthonormality also exists. Okay, so let's come back to this upper triangular matrix representation and see a very interesting result about orthonormal basis in inner product spaces. Supposing you have an arbitrary vector space, at this point I am not saying inner product space, vector space, and you think of an operator T, okay, and you have a basis. We always think of a matrix for that operator in that basis B, right. So, we know how to do this. We know this very nice result about upper triangular matrix representations, but what do upper triangular matrix representations really mean? This matrix will be upper triangular if and only if the span of V1 to Vj, for every j, the span of V1 to Vj should be invariant under T. Okay, so this is an interesting way of characterizing the upper triangular matrix representation. So far we have just said upper triangular, but what does it really mean in terms of what the operator is? It turns out this is what is important. If over a particular basis the operator has an upper triangular matrix representation, this is an if and only if condition. Okay, V1 to Vj, it has to be invariant under T. Okay, so the proof is not very hard. I'll just write down the matrix for you and you'll see the proof will sort of follow. If your matrix is upper triangular like this, you can see if you take the first j coordinates and you do linear combinations with them, only the first j are going to be non-zero, right. So, there is invariance sort of with respect to that, but bottom part is 0. And the other way also is true. If you have a basis in which the first j alone are going to be involved, if you express the operator in that basis, you will naturally get an upper triangular representation. Okay, it's a very simple characterization of what it means to have an upper triangular matrix representation. Okay, so this sounds very simple, but it's very important. So, now you will see a lot of things will come together because the span of V1 to Vj has to be invariant under T. So, this is the condition that's important. Okay, we have seen before that every if you have over the complex field, when you have eigenvalues, when you can have eigenvectors over the complex field, any operator has over a vector space over complex numbers has a upper triangular matrix representation. Okay, so that we have seen before, right. So, we saw one of the results how to get an upper triangular matrix representation for a operator in a complex vector space. What about orthonormal basis? Okay, can you have an upper triangular matrix representation with an orthonormal basis? That's a great question, right? And the answer is yes, and that's what's called Schur's theorem. Okay, so this is a very popular idea, very important theorem. If you have a finite dimensional inner product space over C, over the complexes where you have eigenvalues and eigenvectors and all that, and you have an operator T, it turns out there exists an orthonormal basis such that the matrix of T with respect to B is upper triangular. Okay, so that's a powerful result. It's called Schur's theorem. And the proof is actually, we've already seen the proof, it's not very hard to see. Okay, we know that there exists a basis in which T is upper triangular because it's over complexes, right. So, eigenvalues, eigenvectors exist. So, you can use that and make an upper triangular matrix. Now, you take that basis in which it's upper triangular and simply run Gram-Schmidt on it. When you run Gram-Schmidt on it, you get an orthonormal basis. Not only that, the span of E1 to Ej is the same as span of V1 to Vj. Okay, so span of V1 to Vj is invariant under T. Span of E1 to Ej is also invariant under T. So, the matrix with respect to E is also upper triangular. Okay, and that's the end of story. Okay, so look at this very nice result that we have now already. If you have an inner product space, we know that there are these orthonormal bases. An orthonormal basis simplifies the description of the coordinate system, simplifies operating with vectors, etc., etc. That we will see more and more later on, but as it is, you can easily be convinced that that's true. Okay, so we saw before that in a vector space where eigenvectors, eigenvalues exist, you can have an upper triangular matrix representation, vector space over complex numbers. Now, because we have an inner product space, right, you can have an orthonormal basis in which the operator will have upper triangular matrix representation. Okay, so that's very nice, it's very convenient and good thing to have. Okay, so we can work with orthonormal basis in an inner product space and not really lose anything that is significant. Okay, so that's a nice result to have, and I'll stop here for this lecture and pick up from here in the next one. Thank you very much.